All right. Physics 252 Project 1, designing CubeSats. You know, I guess everyone else who's taking this course already knows what the heck those are. But they're small satellite-esque cubes that have like recording data or like a camera or anything. So the whole point is to maximize the amount of interior space while minimizing how much space these rotation wheels take up, assuming that you've covered the outside of said CubeSat in something like solar panels or something that is going to assist in powering the device so that it can send signals back down to Earth for data collection, much like the one that Oregon is setting up. So in this case, we need to first orientate the CubeSat in space. Say you want to put a camera facing, down. Like if there was a camera off to the side here, you want that kind of facing towards the Earth. So in that case, we're going to first have to determine the CubeSat's moment of inertia. In this case, it's technically a flat slab. It's just more of a cube than a slab. So we can use the moment of inertia equation that is 1/2 m a squared plus b squared, a and b being the width and height. Assuming that's per axis, so technically there's going to be 2 of these, because we also have, 3 of these, because you also have to take into account the x, y, and z axis. But we only need 1 per axis that we're rotating. In this case, m, of course, is naturally going to be the mass of the CubeSat, and a and b are going to be the dimensions. They're going to be in meters, although the CubeSat is so small that we actually use centimeters to measure it. But for the equation to work, we need to use meters. So in order to rotate the CubeSat, I've thrown up this little rudimentary design here. If we use hoops, which have a moment of inertia ring of I is equal to mr squared, it maximizes how much of the mass is effectively, being involved in this rotation. So if we rotate that around a single point in the middle, this becomes, you'll notice in the main CubeSat that ends up being 1/12. If we use a hoop, we have an equation of I equals mr squared. That ends up being a much higher value. For example, if we use like 100 grams of tungsten, that's just something I assumed with a radius of 4 centimeters. That has a moment of inertia that is 0.0016 kilograms per meter squared, which would be a little bit larger than the overall CubeSat, making it a little bit easier to rotate. Now, in order to rotate our CubeSat, it's not really thinking of spinning the reaction wheel, because when we start spinning the reaction wheel, we're actually rotating the CubeSat around this, we'll call it stationary, although it's moving in space. Imagine if the wheel was stationary, thanks to the torque pointing in this direction vector. If we move the CubeSat, if we want to move it around the x-axis, which is going to be our up and down in this diagram here, if we rotate the reaction wheels in the opposite direction, that's going to counteract the acceleration and start moving the overall CubeSat in the same direction. So, essentially, if we start accelerating this direction and then start slowing it down by accelerating the opposite direction, that is going to cause our CubeSat to follow kind of a graph like this. And that's because we're going to start rotating up. We're going to get up to speed. About halfway through, we're going to start rotating in the opposite direction, which will then cause the CubeSat to zero out when it reaches 45 seconds. And that's derived by this angular velocity chart here. So this equation here calculates the moment of inertia of our reaction wheel and how fast we have to be spinning the reaction wheel, which is our velocity chart here, in order to get it to spin over time. This graph here represents that spin over time, and then this is rotations per second on the side here, time in seconds on the bottom. So the overall graph represents a rotation divided by time squared, which is the angular velocity formula. Now, of course, to calculate the minimum torque, in this case for part 4 of our CubeSat experiment, it does ask us, not part 4, sorry, part 3D, the maximum power of the motor. We need to know the torque, because the easiest way to convert to power is to convert to watts, which is Newton meters per second is equal to 1 watt. So we know how much our moment of inertia is, and we know how much that is in Newton meters. It's a simple conversion of about 100, so it ends up being about 0.0157 Newton meters to get this thing to rotate the moment of inertia. So the minimum power in wattage is going to be our moment of inertia divided by our time, because it's Newton meters per second. We have Newton meters divided by seconds, and we get a wattage of 0.003 watts to get the thing moving. And that is the end of my explanation.